All right, so part 2 of families of algebraic functions. Now let's move on to rational functions. So rational functions have the general form f of x equals p of x over q of x. So it's a ratio of two polynomial functions. And to avoid confusion, we'll label the top one like we did with polynomial functions, and the bottom one will have different subscripts and a different letter to indicate the power, the degree of that polynomial. All right, so it's a ratio of polynomials. This is the degree of the numerator. This is the degree of the denominator. Sometimes they're the same, sometimes they're not. Okay, so general properties. First of all, the roots of q of x, so of the denominator, determine either vertical asymptotes or holes in the domain. So, in other words, the domain in every case is the set of all real numbers such that the denominator is not equal to 0. And you can use that to check the domain of any rational function. The multiplicity of roots for q of x will give you symmetry across the vertical asymptotes. So, in short, we get two cases. So I'm just highlighting right now this vertical line here is a vertical asymptote. So is this one. So in the odd case, odd multiplicity of a root, we have the function appearing to get closer and closer to on one side of the vertical asymptote, but not. So it'll get very negative or very positive, and on the other side, the opposite behavior. So they look like 1 over x near the asymptote. On the other hand, if the multiplicity is even, then they get closer and closer on either side to that vertical asymptote, but going in the same direction. So either extremely positive or extremely negative. Those are just some examples. And rational functions, of course, can have much more complicated behaviors than polynomial functions. All right, so some other important information. We do get horizontal asymptotes sometimes when either the denominator has a greater degree than the numerator, or they are equal in degree, okay? And we obtain slant asymptotes when the numerator is exactly 1 more than the denominator. And we use polynomial division to figure that out. All right, now we're going to get into algebraic functions generally. Up until this point, we've just been discussing the various different subfamilies of algebraic functions. But here, we're going to just do some examples because this is a category far too broad to discuss in any considerable detail. And in fact, we'll have to go on a case-by-case basis almost all the time. So, number 1. So for each one of these functions, we're going to describe them as best as we can using the tools that we have right now, and graph them and sketch the graph. So we have y equals the square root of 1 plus x all over x. So this isn't a simple function like the other ones. There's a combination of things going on here, but we're still using only algebraic operations. So first of all, some things to note. We have a vertical asymptote at x equals 0. So you can't plug in 0. That means the domain excludes that. But also, the domain for this particular function is all real numbers except, again, x can't be 0, and the argument under the radical, the radicand, has to be greater than or equal to 0. So we need to be able to solve or simplify this domain in terms of interval notation. So let's take these into consideration. So first of all, 1 plus x greater than or equal to 0 means x is greater than or equal to -1, and x is not equal to 0. So what we're actually looking at is the interval -1 to 0, and then open parentheses, and then from 0 to infinity. So that is the domain. And for very large values of x, we have a horizontal asymptote of y equals 0. Here's the graph of this function. So you'll have to take my word for it that it looks like this, but it passes through the point -1, 0, and then it looks like this. So remember, this is a vertical asymptote, this x equals 0 line, and as we move further and further to the right, it will approach 0 as well. So the curve flattens out and we'll get closer and closer to y equals 0. All right, let's move on to another example. Let's consider the function f of x equals x squared. Oops, let's write that a little bit more clearly. Minus 2 plus 1 over x minus 3. One way we want to think about this is, fundamentally, this is a rational function and we can express it as such. But really, we want to think about it as something that's almost polynomial. So this is a polynomial part. And then this term comes and messes everything up for us. So this looks like 1 over x. It's just shifted. We'll talk about that in a later video. But so let's talk about what we have here. So we have a vertical asymptote at x equals 3, right? That's pretty clear. We can't plug in 3. And it looks like a parabola interrupted by that vertical asymptote. So the graph, again, you'll have to take my word for it, but you can go ahead and use Desmos if you'd like, looks something like this. So here's x equals 3. There's that vertical line, okay. And it passes through a couple of interesting points. We pass through negative root 2, 0, pass through root 2, 0, and then another point somewhere down here. But fundamentally it looks like, oh, and it also passes through another point over here. And then it continues like this. So you can see how if it wasn't for this part of the graph, right? So, or maybe let me circle like this. That part of the graph is the discontinuity. Again, I'm using a word that I should be using right now, but it's the part of the graph that is the rational part, the one that looks like 1 over x, but it interrupts the parabola. Okay, third example, and this is one that comes up quite a bit. So we have r of t equals the square root of 1 minus t squared. Again, not a lot going on here, but interestingly, this is the upper half of the unit circle. Yes, that one, the unit circle. And its domain is -1 to 1 inclusive. So of course it looks like an upper half circle. So here's the point 1, 0, the point -1, 0, 0.01, and the graph goes right through those points looking like a semicircle. So not the best picture, but you get the idea. Again, we'll be using this quite a bit. All right, so time for you guessed it. You know it and you love it. You try it. All right, so, and again, I'm not collecting this. I just want you to try your hand at developing these skills. So sketch the graph of y equals 1 over 1 minus the cube root of x. And note the domain and range. So I would like you to provide the domain and range. And you can use any of the techniques that we've discussed here. So you can, plug some points in, try to figure out where a vertical asymptote would be if there is one. Find a y-intercept, find x-intercepts, all the above.